Hello. Thanks for clicking on another Anarculus production. Today is another exciting event as we will be talking about our second theorem of the year, the intermediate value theorem. It's everyone's favorite theorem if they enjoy intermediate things. Okay, so today we're going to be talking about the intermediate value theorem. All right, our second theorem, first one where we're going to have to do a lot of analysis. Okay, so let's start actually with an activity. All right, we'll start with an activity. The activity is a pretty simple one. Basically, what I want you to do is I just want you to sketch a function with the given characteristics. So read the four characteristics and sketch a function that would satisfy those characteristics. Okay? All right, so I'm going to do it also so that at least you have an idea, something to work with if you're having trouble. Okay, so it's got to be sketched on a closed interval a to b. So that means it's going to include a and include b. X equals a, it must be above the x-axis. So here you go. At b, it's below the x-axis. So here you go. The graph that I draw must be a continuous function when sketching from x equals a to x equals b. So it's got to be continuous. So we talked about that in the last section. Continuous meaning no jumps, holes, gaps, or asymptotes. And also, although we take it for granted a lot, the word function is in here, okay, which means that it has to pass the vertical line test, whatever you drew. Whatever you drew has to be continuous, no jumps, holes, gaps, or asymptotes. And I'll just draw this, it doesn't matter. And there we go. Okay, there is my function, or there's my graph of f of x. All right. Now, I do have a question for you. Okay, I need to know, hopefully, you can tell me. Well, you can't because I'm not actually there when you're watching this, but it's okay. I need to know, okay, I need you to look at your graph and decide whether or not your graph went through the x-axis. I don't care where it went through the x-axis. Mine looks like it went through here, so pretty close to the origin, but it doesn't matter. Okay, but it went through the x-axis. Okay, everyone's graph should have gone through the x-axis at least once. Now, it's possible you could have gone through more than once, right? I mean, you could have drawn this, right, or something like that. You maybe went through more than once, but you have to go through at least once, okay? Everyone should have gone through at least once, and if you did, what you've done is you've just proved a weak version of the intermediate value theorem, okay? All right, so let's talk about what the intermediate value theorem says, and then what exactly we can do with it, and how it might work. Okay, so here is the intermediate value theorem. Now, this is quite a mouthful from the previous slide where I said it goes through the x-axis, right? It says, and you can read it along with me, if f is continuous on a closed interval a to b with f of a not equal to f of b, and k is any number between f of a and f of b, then there exists at least one number c on the interval ab closed such that f of c must equal k. And that is the intermediate value theorem. Okay, so now what we're going to do is we're going to analyze the theorem. All right, just like kind of like we did the squeeze theorem. All right, but we really do need to talk a little bit about this because this is not necessarily obvious, I'm sure, to many of you just by looking at it. Okay, so let's start with the first thing that maybe hopefully you notice is we're talking about another theorem, and we did this the last time with the squeeze theorem too. It's a conditional statement that you learned back in shapes class. If all of this is true, then this is the conclusion that we can make. Okay? All right, so to convince yourself that the theorem is in fact true, what we're going to do is we are going to take all of the stuff in the if part of the statement and we are going to try to draw a picture using all of it. So here we go. Okay, I'm going to put my picture, make my x-axis a little bit further down so it's easier to see. All right, so here's what we have. We have f, so that must mean the graph's a function, okay? Because they're calling it f, right? And then later on they use f of a and f of b, right? So I must be graphing a function, so it has to pass the vertical line test. This graph has to be continuous, no jumps, holes, gaps, or asymptotes in it. And the interval that we draw it on must be closed, a to b. Okay, so let's start with the closed interval part, because that's probably the easiest part. A, B. Now, it's got to be closed. There's got to be a point on A and a point on B somewhere. Now, it doesn't say where it has to be, right? A minute ago, I told you one has to be above and one has to be below, but it doesn't say that in the theorem, so we really can put it anywhere. Okay? All right, so there we go. I'll just put my 2 points there. It didn't say it has to be above and below, so I'm going to put both of them above. That's supposed to be allowed. But it does say that f of a can't equal f of b, right? So the two y values can't be the same. So you can't have a y value here and here, then f of a would equal f of b, and that's no good, right? This is my graph of f of x. All right? So now what I'm going to do is I'm going to draw a function that's continuous. All right, so let me draw a function that's continuous. Okay, I'm not going to make it fancy, but maybe we'll do that. Doesn't matter, you can draw anything you want. All right, so there's my f of x. It's a continuous function, so everything on the top here has now been satisfied, right? We're assuming all this stuff is true, okay? So we've taken care of everything that's up there. Now, let's talk about this. K is any number between f of a and f of b. So the first thing you have to do is decide what k is. K is either an x value or a y value, but it's referring to k as a number between f of a and f of b. So, like for example, this must be f of a, right? This is the y value at a, and this number is the y value at b. Okay, so here's f of a, here's f of b. K is somewhere in between it. It doesn't say halfway in between. It doesn't say that. It just says it has to be somewhere between it. All right, so I'm going to put k here. Okay, k. So I put k there. All right, so that's it. That's everything that we can say must be true. There's k, my number between f of a and f of b. I have a closed interval, 2 points, a point on a and a point on b. I have a function that I drew that's continuous, and the two y values at a and b are not the same, right? They're in different spots. Then, here's the conclusion that I can make based on my picture. There is at least one number c on the interval AB. All right, so let's talk about what c is. Okay, c is on the interval a to b, which means that c is an x value, right? C must be an x value because here's a, here's b. C is an x value. All right, so let's put c on here somewhere. Okay, but we're going to put it somewhere specific. It's in a place such that f of c is equal to k. So what does that mean? Well, that means that if I pick c and put it in the right spot, the value of f of c will equal k, right? The value of f of c, if I take c and plug it into f, what do I get? I get this point on the graph, which is k. All right? That is the intermediate value theorem. So sure enough, this did happen. There was a place where f of c was equal to k. Right here. Okay? Right there. That is the intermediate value theorem. Now, here's what I'm saying to you, and I'm going to do this with numbers here in a second, which will make a heck of a lot more sense, I promise you, okay? But it's important to understand the theorem itself, all right, and how it works, okay, with all of the notation as opposed to just numbers. All right. So here's exactly what this thing is saying. It's saying something that's probably as easy as possible. Look, if you have, here's f of a. Let's say f of a, let's say this value for f of a was 10. Here's f of b. Let's say this value was 2. And now I want to go from this point to this point. Then if I want to go between these 2 points, the only way for me to get there is to go through all of the y values that are between 10 and 2, right? I have to go through 9, 8, 7, 6, 5, 4, 3, 2, right? To get down to 2, correct? I have to. It's the only way to do it, right? It's the only way to do it. So I have one endpoint at the y value 10, another endpoint at the y value 2. Then as long as I pick this number k between 10 and 2, well then yeah, of course there's going to be a place where the y value is equal to that. I could make this value of k 4. I could make it 3.74. I could make it 8, right? I could put it up here if I want. It doesn't matter. Is there going to be a value of c between these two x values such that it's going to equal k? Sure. Now in this case, it's this one, right? If I put it here, well, now it's this x value. It's still between a and b. That's c, right? So basically what the theorem says is, okay, if you have two endpoints at two different y values, and the function is continuous and different, I'm sorry, the function is continuous, I'm ahead of myself, I'm on chapter 2. The function is continuous, and these conditions are true, then you have to pass through all of the y values between the one and the other to get from one place to the other. All right, that's the intermediate value theorem. So what I said earlier was that the little activity that we did, where we went through 0, that is a weaker version of the intermediate value theorem. It's weaker because it's asking you, does it go through the x-axis? Well, yeah, it goes through the x-axis. It went through the x-axis because you put 1 point above the x-axis and 1 point below the x-axis. But the intermediate value theorem says something stronger than that. It says, yeah, you're going to go through the x-axis, but you're also going to go through all these other y values between these 2 points. Not just the x-axis, not just 0, but the x-axis is a nice place to look at because you can see it on the graph. Okay? That's what the intermediate value theorem says. All right? Now, what's important about theorems, and we're going to go on here and talk about a couple of examples, is the theorems in this course in calculus, especially on the exam, they don't necessarily, well, they care about the answer. Can you use the theorem? But their definition of use the theorem is not just, can you plug in numbers and see what you get? Their definition of the theorem is, do you understand what must be true before you can even use the theorem? Okay? Do you understand the qualifications of the theorem to be able to use it? And we're going to see that here as we go. So here's a perfect example. Use the intermediate value theorem to show that there is a 0 for the function f of x equals x cubed plus 2x minus 5 on the interval 0 to closed. Okay? So we want to use the intermediate value theorem to show that there's a 0. So by 0, we mean that the y value will equal 0. So basically, I'm asking you the same question I did in the activity. Will you go through the x-axis? Okay? So to figure out if you're going to go through the x-axis, right, using the intermediate value theorem, you need to convince me of a couple things. You need to figure out what f of 0 is. So f of 0 is 0 cubed plus 2 times 0 minus 5. It's negative 5. And then I need to know what the other endpoint is. So that's 2 cubed plus 4 minus 5, which is going to be 8, 4, 12, 7. Okay, so what do I have if I draw a picture? You don't need to draw the picture, but I have a point here. Oops, nope, that's not where it belongs. Okay, so I have a point on 0, -5 here, and then I have a point on 2, 7. So here's 7, here's 2, 7. Okay, now the question is, will I go through the x-axis, right? It certainly appears that way. However, remember the if part of the intermediate value theorem. Look back on your paper. All right, I don't want to go back on here, but look back on your paper, okay? The if part of the intermediate value theorem says something very important. It says that f has to be continuous on 0, 2, right, on the interval. If it's not continuous, well, maybe there's a hole here at the x-axis. How do you know? So maybe there isn't a place where that graph goes through 0 because there's a hole there. Unless you convince the reader that the function is continuous on the interval 0, 2, you can't use this theorem. You must convince them of this before you can start trying to use this. Okay? You must convince them of this before you can start using that theorem. Because if it's not continuous, the theorem never applies, right? The theorem doesn't apply. It doesn't work. Okay? So I know that f is continuous on 0, 2 because f is a polynomial. And all polynomials are always continuous. Okay, they're continuous everywhere. I mean, you could even say, hey, listen, there's no denominator, so there's no place where f would be discontinuous. So f must be continuous on 0, 2. Fine. You can say that, but you have to say this. You have to state it. You can't think of it in your head. You have to write it down. Okay? Unless you say this, if we're on an assessment or something like that, and I ask you to use the intermediate value theorem, if you don't say to me f is continuous on whatever interval that is, okay, to begin with, before you use the theorem, you just take the numbers and plug them in, it's wrong. I'll mark it wrong. It's not right. Okay? Because if that thing wasn't continuous to begin with, you could never have used the theorem. All right? You could never have used the theorem. Okay, so our final conclusion is, yes, there is a 0 on 0, 2 because f of 0 is smaller than 0, which is smaller than f of 2, right? We have this inequality here, right? 0 is between f of 0 and f of 2, and you showed me it was continuous. So then there must be a 0 by the intermediate value theorem. Okay, by the intermediate value theorem. All right, that's how it works. Okay, we'll try one more. Oops. Same thing. Use the intermediate value theorem to show that there's a value of c such that f of c is equal to 9 for that function on the interval -1 to 4. Well, again, I want to use the intermediate value theorem. The first thing I need to convince the reader that f is continuous on -1, 4 because f is a polynomial. And that's really all you have to say. The readers are all AP Calc teachers, or calculus teachers, so they understand that if you know f is a polynomial, then it's going to be continuous. Okay? So f is in fact continuous there. All right, now, next step. What do I need to do? I need to establish where my endpoints are. So f of -1, it's going to be -1 squared plus 2 times -1 plus 5. Woo. or minus 5. We got 1 minus 2 minus 5. 1 minus 2 minus 5 is negative 6. And then we have f of 4, which is going to be 4 squared plus 2 times 4 minus 5, which is going to be 16 and 8 is 24. 24 minus 5 is 19. Okay. Now I want to find a value of c such that f of c is equal to 9. So again, if you want to see it in picture form, at negative 1, you're at negative 6. And then at 4, you're at 19. So the question is, will the y value ever be 9? Well, f is continuous, so yeah, of course it's going to be 9. You got to go from this point to this point. You got to go through y equals 9. So the answer is yes. Okay. Since f of 1 is less than 9, which is less than f of 4, then f of c must equal 9 by the intermediate value theorem. And that's all there is to it. Okay, that's how the theorem works. But what's important is you need to understand, right? You need to understand that there are conditions in the if part of the statement that have to be true before you can just use the conclusion, right? In shapes class, you learn theorems all the time. But pretty much what you wanted to do is, well, just tell me what the conclusion is and I'll use it, right? If I give you a circle and 2 tangents to the circle intersect, then I know that these are equal to each other, right? That's a theorem, okay? But what would you do? Well, this says 3x, this says 5x, or 5x plus 2. You'd set them equal and solve it. You wouldn't think about the fact that it's a theorem. But here, okay, in college mathematics, this is what we want you to be able to do, all right? All right, now finally, okay, I actually wrote it up here as a slide, but I'm going to make it a question. Let me erase that. I'm going to make it a question for you to answer on Edpuzzle. I want you to work on this question here. Use the intermediate value theorem to show me that there's a value of c such that f of c is equal to 2 on that function on that interval. Okay, so you probably have to write the problem. You may have to write it down because I think the video is going to pause and it's going to take this off the screen. So write it down, and that's what I want you to do, and then you're going to respond to that for me. All right, good job today. Thanks for clicking. Enjoy yourself. See you next time.